Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome this morning. Today, I have the pleasure of introducing Alexei Gotsman, who has been working at the University of Cambridge with several people that we know quite well, including Byron Cook and so forth. And the title of his slide is also one that contains words that all of us know very well, and working with heaps and concurrency and verification and things like that. So I'm looking forward to a really interesting talk. Welcome.
Okay. So this talk is going to be, the area of program verification, where the goal is to formally prove properties of programs. And there are several reasons for doing this. The first most obvious application is...
Can you turn the microphone on? I'm sorry. It's the...
how?
There's a little button on the top.
Okay. So the first most obvious application is development of safety-critical and security-critical software, where the cost of software bugs is just too high. Recently, program verification has also been applied to ensure reliability of mainstream software, to prove that software like device drivers, for example, didn't have certain types of bugs in it. And more broadly, figuring out reasoning methods for software can actually suggest better ways of designing programming languages or new programming methods. So program verification is useful. Now, in this talk, I'm going to talk about a restricted class of programs called concurrent programs with heap. And as with any verification problem, there are a couple of ways to address this verification goal. For example, we might want to verify software using program logics. So these are specialized proof systems for reasoning about programs. And the idea here is that you prove properties of programs by constructing formal derivations in these proof systems by hand or in an interactive theorem prover. Then there are program analyses. These are automatic tools that would take your program and analyze it according to some algorithm to check if it satisfies a given property. So really what we have is a spectrum of verification methods, and program logics and program analyses are kind of at the ends of the spectrum. So on one end, we have manual but very powerful techniques that are able to verify very deep properties of software. And at the other end, we have automatic but weaker techniques. And so when I develop a verification method, ideally, I would like to get the best of both worlds. I would like to get tools for both manual and automatic reasoning. And as I'm going to show you in this talk, for this particular class of programs, this is a bit non-trivial. So it may be quite hard to devise a method that can be implemented both as a program logic and as a program analysis. And that's because for this class of programs, principles of reasoning that you would use to verify programs manually or automatically may differ in subtle ways. Okay, so before I go on to describe my results, let me just briefly introduce the area and talk about why verification of this class of programs is challenging. So first of all, I'm going to talk about heap-manipulating programs. So this is an example of a heap-manipulating program where what happens is this piece of code traverses what happens to be a cyclic double-linked list. And when it finds an entry in this list with a particular value of the key, it removes the entry. So this code is heap manipulating, so we might want to verify some properties that are concerned with heap manipulation. For example, we might want to verify that this code is memory safe, meaning that you never dereference a memory cell that's not guaranteed to be allocated, and that the program containing this code doesn't have memory leaks in it, that is, it disposes all the memory that it allocates. Now, it happens that to do this, we'll have to know that, for example, at this point in the program, this node guy points to a well-formed cyclic double-linked list. And that's because these two statements here are going to try to delete an entry from the double-linked list. And if this pointer doesn't point to a well-formed date structure, they will dereference unallocated memory and the program will crash. So you basically need some kind of information about the structure of the heap. And this information is not something that your type system is going to give you or that a shallow pointer analysis could give you. So you really need some kind of specialized program analyses to recover this information. So these program analyses are called shape analysis. That's because they discover the shape of the heap during program's execution. So shape analysis is a tool that would go over your program and at every point in the program tell you how the heap looks like. Okay, so it happens that actually you need this kind of information not only to verify these memory-related properties, but also to verify all kinds of other properties. For example, if you want to prove that this loop terminates, then you will have to ensure that the list it traverses is cyclic. That is, you will eventually hit the same hit the head of the list again when you're traversing it and get out of the loop. So to prove termination of liveness properties, you need to know shape information. Same goes for, say, some security properties. If you want to ensure that some information flow properties, then you have to know how the program stores the data it manipulates in memory. And of course, same goes for functional correctness. Okay, so that's shape analysis. Now, this program is sequential. So let's see what happens when we go to concurrency. Verification of concurrent programs is challenging, and that's essentially because the naive way of verifying concurrent programs leads us to consider all possible interleavings or schedules of threads in the program. So in your reasoning, at every point in the program, you will need to do a case split on which thread gets to execute. And in a program analysis, this just leads to a state space explosion. There are just too many states to consider. In a program logic, this leads to intractable reasoning. You just lose track of what's going on. And unfortunately, heap manipulation only makes things worse because it expands the set of possible thread interactions. And we can't ignore this problem because multicores are here and software is going to become more concurrent. Okay, so what do we do? Well, one possible solution is to use so-called thread-modular reasoning techniques. The idea here is that instead of considering your program as a whole, you consider every thread in it in isolation under some assumption in its environment. So you will analyze every thread separately, and there's going to be something in your reasoning that captures the possible interference from the other threads. And then from several analyses like this, you're trying to infer the properties of the whole program. So this is a good method in that it avoids direct enumeration of interleavings. But it may be quite challenging to devise these thread-modular reasoning techniques for heap-manipulating programs. And that's because it's very hard to summarize this interference concisely when you don't know which thread is going to modify which part of the memory. OK, so now given that, let's see what we have in stock for verification of concurrent programs with heap, the mixture of concurrency and heap manipulation. So in the world of automatic tools, in the world of program analyses, we have a very good infrastructure for sequential shape analyses. There are quite a few of these analyses, and they're getting better by the day. But the main method of handling concurrency is by enumerating interleavings. So in the end, you get unscalable tools. Now, in the world of program logics, in the world of manual tools, we have some interesting thread-modular reasoning principles, in particular in something called concurrent separation logic that I'm going to talk about here. But these logics handle only toy programming languages, for example, without dynamically allocated synchronization primitives or dynamic thread creation. And so in the end, you get manual proofs of toy programs. So really, there is a gap here that would be nice to bridge. And what you really want is a thread-modular shape analysis for concurrent programs, an automatic and scalable tool that I could use to verify software. And then when a shape analysis tells me that the program is correct, it's very good if you can somehow check that it is. So it's good if the shape analysis produces a certificate of some kind. For example, this might be a proof in some program logic that confirms that the answer that the shape analysis gave me is correct. And this is useful for multiple reasons. But for example, you could use this proof in a program logic in a proof-carrying code system or in an interactive theorem prover. And my main contribution is just an analysis like this. So it's a thread-modular shape analysis for concurrent programs. First, I developed it for a very simple concurrency model. And later, I extended it to handle more realistic features, such as dynamically allocated locks and dynamically created threads. And this analysis is also interprocedural, so it handles our first-order procedures. So this work, an interprocedural analysis, was actually done at first in the context of sequential shape analysis. And was quite useful there, but it also interacts with concurrency in a nice way. And finally, as I've said before, shape information can be used to verify other kinds of properties. And I've also applied the methods I developed here to verify liveness properties of non-blocking concurrent algorithms. And non-blocking concurrent means that it's a particular class of algorithms that use low-level synchronization techniques. And to do this, I actually had to develop a prover for verifying liveness properties of sequential C programs. OK, and as I've said before, logics and analyses play together here. So really, every one of these analyses that I have comes with a program logic that uses the same reasoning principles. So you get the tools both for manual and automatic reasoning. OK, so in this talk, I'm going to concentrate on one slice of these results, which is I'm going to talk about the thread-modular shape analysis in a simplified setting and its connections with logic. And I'm going to also talk about how the logic and the analysis can be extended to handle dynamic log creation. OK. So before I go on, I should just briefly describe something called concurrent separation logic, which is a program logic that this analysis is based on. So let's see. Separation logic is a Hoare logic. What this means is that it manipulates logical statements of this form, where P describes the state of the program before executing the command C, and Q describes the state of the program after C terminates, if it ever does. So P is a precondition and Q is a postcondition. So concurrent separation logic handles heap-manipulating programs with static locks and threads. What I mean by that, for the purposes of this talk, is that your program consists of one top-level composition of several threads, and these threads synchronize using a finite number of predetermined non-aliased locks. So you have one top-level log declaration. Now, I won't present you the logic in detail, but the main idea that you use to reason modularly about heap manipulation here is you partition all the allocated memory in the program into several parts. Now, some parts are thread local. What this means is that, say, this part is local to thread T1. This means that only this thread can access this part. Some parts are protected by free locks, locks that aren't held by anyone at this point. For example, this part is protected by lock LK1. And what this means is that a thread can access this part only after it has acquired the lock. Now, what I should say is that this view is not something that the runtime system or a compiler enforces. It's something that is enforced by the logic, by the proofs in the logic, to make it easier to reason about programs. So in particular, it's not going to be true of all programs, only the programs that the logic can verify. OK, now the way we reason about this picture evolving in time is we associate, as a part of a proof of our program, with every lock a resource invariant, ILK, that tells me how the part of the heap protected by the lock looks like during program's execution, in the cases where the lock is free. So for example, this is just a predicate on heaps. For example, it might say that the lock protects a single linked list starting from the variable age. So this means that this partition looks like this when the lock is free. And now the way the logic reasons about concurrency is using these axioms for lock and unlock commands. So let's see. What the axiom for lock says is if I have a lock command executed, well, for example, by the thread T1 here, then P will describe the local state of this thread before it executes the lock command. So P is the local state of T2. And then what happens after the thread executes the lock command, logically, it gets the ownership of the part of the heap protected by the lock. So the shared part protected by the lock gets conjoined to its local state, and now the local state of the heap becomes P combined with the resource invariant for this lock. So this is done using this star connective called separating conjunction. What it does is it combines two heaps with disjoint sets of allocated cells in them. So when I acquire a lock, I get the ownership of the shared state. Now, the unlock command works the other way around. It requires you to have the ownership of in your local state of something that satisfies the lock's invariant. And after you execute the unlock, you lose the ownership of this part of the heap. So now the local state of thread T2 becomes smaller. Now notice that the boundary here and here may actually be different. That's because the thread might have transferred the ownership of some cells in between lock and unlock command into the resource invariant, for example. This is fine as long as the protected part still satisfies the resource invariant. So this picture may change in time. And as a forward pointer, actually the logic doesn't allow all possible resource invariants. These invariants have to satisfy certain constraints. And this is going to be the source of future discrepancy between the logic and the analysis here. So I'll describe this later. OK, so now given this idea of reasoning about concurrency, let's try to design an automatic tool that uses this principle. So what I'm going to show you is an analysis that takes as an input a concurrent program with log-based synchronization. So for now, I'll assume that we have static locks and threads. That is, the program looks like this. And in general, we can handle dynamic lock creation and dynamic thread creation. And as an input, the analysis is going to take an arbitrary, to a degree, sequential shape analysis, shape analysis for sequential programs. There are some conditions that this analysis is going to have to satisfy that I won't have time to go into. But at least it has to be based on abstract interpretation. It's constructed in a particular way. Now, as an output, what the analysis will give you is it will infer for you the resource invariants for the logs. And it will infer for you the local states of all threads at every program point. So at every program point in the code of this thread, the analysis will give you some information about how the local state, the local heap of this thread looks like during the program's execution. And as a byproduct, the analysis will prove memory safety and data race freedom of this program. And since the analysis is thread-modular, its complexity is actually linear in the number of threads, so it is scalable. OK, so here is the bird's eye view of the analysis. What the analysis will do is it will take some initial approximation of every resource invariant for every log, which at the moment I'm not going to tell you where I get that from, but suppose we have it. And the analysis is going to construct an increasing chain of approximations to this resource invariant for this log until this chain stabilizes. So by increasing, I mean that the next element in the chain describes more states than the previous element. Okay? And the way the analysis will move from one element in the chain to the next is it will analyze every thread in the program, assuming, taking the current approximation ik of the resource invariant as the environment assumption, assuming that the other threads respect this resource invariant. And from this analysis, it will infer the new approximation of the resource invariant. So you see there is some kind of a thread-modular reasoning going on here. OK, so now to be more detailed, the way you analyze a thread in this case is, OK, suppose we have this thread and just one lock and some approximation ik of the resource invariant. What we do is we start with some initial local state of this thread. And again, I'm not telling you at the moment where I get that from, but suppose we have it. So I take this initial local state of this thread at the beginning of the program, and I run my sequential shape analysis on the code of this thread starting from this state. So the sequential shape analysis will go off and try to compute the local states of this thread during the program's execution. So I know the sequential shape analysis knows how to deal with every command in the code of this thread except for lock and unlock, because it's sequential. And so I have to tell him how. So I'll just use the intuition that separation logic gives me. So if I hit the lock command in the analysis in the case where the local state of this thread is P, then logically I should acquire the ownership of the shared state. So I'll model this in the analysis by conjoining the current approximation of the resource invariant to the local state. So the intuition here is that I assume the other threads respect the resource invariant, so it must hold when I acquire the lock. Now, if I have unlock statement, say I hit it in a state with the local state satisfying Q, then I have to split the state somehow into two parts, local of Q and protected of Q. The local of Q will become the new local state of this thread. And protected of Q will be transferred to the shared state. So it will become the new state protected by the log. And what I should really do is I should add this protected of Q as an additional disjunct into the resource invariant. And the intuition here is that this takes into account how the thread modified the shared state in between lock and unlock commands. So in this way, I get the new approximation of the resource invariant. Now, the way you split the heap here would be decided by an application, some kind of application-specific heuristic. So depending on the type of applications you're dealing with, the analysis will be set up so that it splits the heap in the right way. So I'm going to show you one heuristic in a second. And just one more thing before I go on. Since I want this process of getting new and new approximations of the resource invariant stabilize, eventually converge, I will also abstract this protected of Q part with the abstraction function alpha of the underlying shape analysis. So this will lose information and hopefully will ensure that the process of discovering new approximations converges. Okay, so here's an example. So suppose we have a program where this log protects a single linked list starting at H. So the resource invariant should say just that. And suppose I have an initial approximation of the resource invariant that says that this log may protect a list of length 1, that is just a cell at the address H containing null. So suppose, okay, I'll run my analysis. Here I will acquire the ownership of this resource invariant. And suppose what this code does in between lock and unlock is it inserts an entry into this list. So now the state Q at the unlock command will look like my old local state plus the modified list consisting of 2 elements. So now I have to decide how to split. So one heuristic that works well, for example, for device drivers, which is one of the applications we consider, is based on variables that correlate with the lock. So these are variables that are accessed only when the lock is held in a concurrent program. And this definition has nothing to do with the heap, it's just about variables. So there are quite a few analyses, both static and dynamic, that can guess these correlated variables for you. And it has to be just a guess, it doesn't have to be precise. Now, if I have the variables that correlate with the lock, for example, in this case, this might be the variable H, then the way I will split is I will take the part of this state reachable from H, that is this list here, and this will become the part of the state that I'm going to give up at this program point. So everything that's reachable from these entry points from the correlated variables goes into the resource invariant. And the rest will become my local state. So here this list will be added as an additional disjunct into the resource invariant. Okay, and actually the way we discover the initial approximations of resource invariants and the initial local state of threads is using heuristics like this. Right, so this is just one heuristic that works for one class of applications. There are more complicated ones, but sometimes they require you to put some additional annotations in the unlock commands telling the system how to do the ownership transfer. Okay, so now if I do this splitting in this way, and then I run the abstraction function over some shape analysis, then what it would typically do is it would say, well, this thing looks like a list to me, except for I know that it has the length 2. Well, let me abstract this and say, well, it's just a list of some length, some non-empty list. And so in the end, starting from this approximation, I get here, which actually describes the answer in this case. So this is a rough idea of how the analysis works. Okay, so that's been implemented, and we used one of the available shape analysis based on sequential shape analysis based on separation logic. The good thing about the sequential analysis is that it's precise enough for most device drivers. So it handles list-based data structures, but very complicated list-based data structures. For example, things like cyclic double-linked lists of a cyclic single-linked list with head pointers, which is a typical data structure that device drivers manipulate. And we basically observed that it's scalable. For example, here we have several dispatch routines of a device driver running in parallel, and then we measure the time that it takes the analysis to analyze them depending on the number of routines that you have. And basically, you don't have state-space explosion because the analysis is thread-modular. And currently, this analysis is part of the Slayer and Terminator tools developed at Microsoft Research Cambridge that check memory safety and liveness properties of device drivers. Yep. So that was FireWire. But these were some, I mean, not the whole thing, just we picked some dispatch routines from it. Okay. Right. So now I've presented you this automatic tool that was inspired by something in the world of program logic. Let's see how this tool actually relates to the logic it was inspired by. And the point of this exercise is that in the end, I want this analysis to generate certificates, proofs in a particular program logic. And concurrent separation logic seems like a good candidate because the analysis basically applies the proof rules of this logic. So does the analysis compute proofs in separation logic? Well, not quite. And the reason is this restriction on the resource invariant I mentioned before. So not all resource invariants are allowed in concurrent separation logic. OK, so what is the restriction? It's called precision. So in concurrent separation logic, resource invariants have to be precise. This is a formal notion, and the definition basically says that a resource invariant is precise if in any heap there may be at most one subheap satisfying this resource invariant. So what this says intuitively is that by looking at the resource invariant and some heap, I have to be able to tell precisely which part of the heap the lock associated with this resource invariant protects. There may not be multiple choices. So for example, a resource invariant saying that the lock protects just the cell at the address age storing a particular value is precise because, well, it protects this cell. But a predicate saying that either the resource invariant is age, or at the cell at the address age, or the empty heap, emp, this predicate is not precise because I don't know whether the lock protects the cell or nothing. Now, the resource invariants computed by the analysis aren't actually precise, and this is due to multiple reasons, but in particular, precision isn't preserved by disjunction, as this example illustrates. And we use disjunction in the analysis, for example, to compute new approximations of the resource invariant. And also, precision is a semantic condition. It's defined semantically, so even if we had, practically speaking, precise resource invariants in our generated by our analysis, we wouldn't have a hard time checking it. OK, so the reason for this restriction in concurrent separation logic is something called conjunction rule. It's a rule that looks like this. It's a standard rule of Hoare logic for sequential programs, and it's also included into concurrent separation logic. What this says is that if I have two specifications of the same command with the same precondition P, that tell me that the command finishes in the state satisfying Q1 and the state satisfying Q2, then surely I should be able to conclude from that that the state that the command finishes in satisfies both Q1 and Q2. So this is kind of a very obvious rule. And it's very useful for combining results of two different runs of an analysis or two different proofs. So for example, the reduced product construction in abstract interpretation uses this rule. And unfortunately, it's not out for concurrent programs. The reason is, well, the catch here is that when you think intuitively about this rule, you think that these assertions P, Q1, etc., they describe the global state of the program. But that's not the case in concurrent separation logic. In concurrent separation logic, they describe only local states of threads. So for example, if I apply this rule in the case when C is an unlock command, then the assertion P will describe the local state of the thread that is executing this unlock command, for example, thread T1. Right? So P describes this local state in both branches of the proof. Now, the treatment of unlock in concurrent separation logic says that I should give up the part of the heap that satisfies the resource invariant. Now, if the resource invariants are imprecise, then I have multiple ways of how to split the heap at the unlock command. So now, here I will have Q1 and Q2 in two branches of the proof describing the local state of thread T1, but this local state is going to be a different part of the heap in different branches. So really, in the two triples here, there is different understanding of what the local state of the heap should be. And so if I can try to conjoin these two guys together with the usual conjunction, I'll get a meaningless result because I'm conjoining two statements about different things. So this is the basic reason for unsoundness. Now,
that you get to that lock invariant by some sort of inference. Whereas if the lock invariant came from the program text, then that would be part of your capital C. So then this discrepancy would not occur. So it's due to the inference that there's a problem.
Not necessarily. So say if I annotate, if the lock invariant is a part of C, right, and I put the same lock invariant in both branches, but an imprecise one, then I can still get an unsoundness because since the invariant is imprecise, it allows me to split things in different ways. So the formal meaning of this is that I can construct a counterexample in the logic that will derive a meaningless triple if the resource invariants are imprecise, even if they are annotated or.
Because you're saying because the unlock allows you then to push back either part of the invariant, even if
is written
So,
down.
so you apply the same axiom for unlock with the same invariant in two different ways in two branches of the proof, and then you will get an inconsistent result. Okay.
And it's when you do that proof step that you decide which one to push back.
Mm-hmm.
That is the logic allows you to choose.
Yeah, yeah.
I see.
And it's useful. You want to choose. Okay. Yep.
Can you remind me, are we just focusing on safety properties so far?
So far, yes. But this is going to be important. Yeah, I'll say a few words about liveness in a moment. Okay. Right. So, okay, so what's happening here? So the analysis results can't be compiled into concurrent separation logic, but the analysis is still sound, one would hope. So what's happening, of course, is that the underlying logic of the analysis is different from concurrent separation logic. It's a variant of it where you don't have the conjunction rule and you don't have the precision restriction. So it happens that you don't actually have a proof of soundness for this logic. Well, first of all, the soundness of concurrent separation logic is a tricky business. The logic itself was devised by Peter Hearn in 2002, and the first proof of soundness was given by another person, by Steve Brooks, in 2004. And this 2-year gap is not due to the fact that the proof is so terribly complicated. It's rather the time that it took people to figure out what's going on, why they're getting unsoundness, why they need precision. And it happens that precision is used throughout the soundness proof of Brooks's, not only for the soundness of the conjunction rules. If you remove it, the whole proof breaks. The reason is that what people came up with to prove concurrent separation logic sound is this construction, where if I want to prove that the logic is sound with respect to the concrete semantics, the usual interleaving-based semantics, then I stick a guy in the middle, which is the thread-local semantics. So this semantics kind of embodies the intuition of concurrent separation logic. It gives the ownership transfer semantics to lock and unlock commands. So at lock, you get the resource invariant, and unlock, you give up the resource invariant. And it happens, in this case, you need precision to define the part of the heap to give up and unlock. To define the semantics, you have to decide what to do at unlock command. And then the way you prove the soundness of the logic is you first prove the logic sound with respect to this thread local semantics, and this kind of gets rid of all the syntactic issues here. You just have the semantics. And then you prove that this reasoning method, expressed as this semantics, the thread-modular reasoning method, is sound with respect to the concrete semantics. Now, what I've done is I've proved the soundness of both the thread-modular analysis and this variant, non-standard variant of concurrent separation logic as one theorem. So using a guy in the middle that's called intermediate thread-local interpretation. So this is similar to thread-local semantics, but it records the decisions about heap splittings taken by a proof or in the logic or a run of the analysis. So it's some kind of a generalization of the thread-local semantics. And in this way, you get the proof of soundness both of the analysis and the logic in a uniform framework. And a consequence of this is that the results of the analysis can actually be compiled into the logic, so you get all the benefits that you wanted. Okay, so now I've mentioned that conjunction rule is actually useful in some cases to combine results of the analysis, for example. So when is it sound to use conjunction rule in the analysis? Well, one case is when, of course, you can ensure that your resource invariants that the analysis infers are precise. And this can be ensured for a very restricted class of programs. For example, when we did work on verifying liveness of non-blocking algorithms, we actually had to use both conjunction rule and something called non-circular relay guarantee rule, which kind of has the flavor of it. And in this case, we were able to get away with it because these non-blocking algorithms are very restricted, very paradigmatic, and we were able to ensure that the resource invariants are precise. But if you don't have precision, then you can also do this. If you require that the heuristics that the analysis uses to split the heap at the unlock commands are semantically deterministic. What I mean by that is that they always compute the same function on the concrete program state. They always split the heap in the same concrete way, no matter what the abstract representation of this heap they're given. So in particular, what they can't do is they can't give different answers for different representations of the same concrete state in the analysis. And it happens that this condition is actually not satisfied by most of the domains by default. but it can be ensured at the price of efficiency, at the price of making the underlying sequential analysis less efficient. And as a result of this analysis, of these two options, we actually get an insight into the concurrent separation logic itself, that really the precision is only one way to ensure the soundness of the conjunction rule. Really, you want this determinism of heap splittings. And the second solution of enforcing the determinism can be taken in the logic by just adding some side conditions to the unlock rule that enforce that you always make the same choice. Okay. Yeah?
Is one alternative not that you don't let the programmer make the choice, that you always just take the disjunction and
that's a very good question. So you might want to say at the unlock command, well, let's take the disjunction of all the possible cases. The trouble is that, well, it makes for one thing, it makes then the release rule can't make the choice, right? What this thing breaks is it breaks the frame rule of the separation logic, unfortunately. And that's because in the frame rule, well, if you think about it, I can show you a counterexample offline, but in the frame rule, you are allowed to pick the frame. And this is really useful when, say, you're doing procedures. At the procedure call, you can split things in an arbitrary way. And if you have this rule and the frame, then you have to say, oh, no, the frame can't do this in an arbitrary way. In the frame, you also have to have a disjunction of all the possible ways to split of things like that. So yes, this alternative, unfortunately, breaks quite a few things. Yeah. Okay. Right. So now let's go to dynamically allocated locks. Okay, so so far we've dealt with a picture like this, where we had one top-level lock declaration, then the threads used these locks. What's happening in reality usually is that locks are dynamically allocated. That is, a life cycle of a lock in a program looks something like this, where I would first create allocation LK at the address LK. Then I would initialize it, that is, convert it to a lock, and maybe allocate some systems data structures that are associated with this log. And then once I do this, I'm allowed to acquire and release the log. And finally, when I'm done with it, I can finalize the log, just convert it to an ordinary location, and dispose whatever systems data structures are associated with it. And finally, I can just dispose this location. And so the challenge here is to now handle this life cycle of a log in the same way that I've shown you before. Okay, so now let's see, the picture of splitting the heap into several parts becomes more complicated. Before, I've had only finitely many parts because I knew how many logs I have. Now I'm going to have an unboundedly many parts, thread local ones and the ones that are protected by some logs. And also, before, every thread knew about the existence of every log. Now, since logs are dynamically created by threads, some threads are going to know about the existence of some logs, and some threads aren't. And so I'm going to have something in my reasoning that would represent the knowledge that, say, the thread T1 knows about the existence of a log protecting this partition of the heap. So there's going to be something extra in the local state of this thread that models this fact. Now, it happens that I will also have that the resource invariants for the log themselves may also contain knowledge about the existence of other logs. It happens that you actually do need this type of reasoning to verify certain classes of examples. Now, I'm going to have to keep track of how many threads or logs know about the existence of some log. And the standard way to do this in program logics is to use so-called permissions. These are numbers that are associated with these log symbols here, for example, 1/2, that intuitively tell me how much of the log I own. So these numbers range from 0 to 1. So for example, if I have half here and half here permission for the log protecting this partition, then what this says is that no one else knows about the existence of this log, since half and half add up to 1. Then the way these permissions are used in reasoning is if I have a non-zero permission for a log, for example, for this one, then this allows me to acquire this log. So for example, now the thread T1 can acquire the log and get the ownership of the partition of the heap it protects, and get also the ownership of the fact of the knowledge that this log, the log protecting this partition, exists. So now it might also acquire this log and get the ownership of this partition. Now, if I have the full permission for a particular lock, the permission 1, so for example here, and I hold this lock, then this means that no one else knows about the existence of this lock and no one else holds it. And this means that I can just finalize it safely. And I know there's not going to be a data race. No one will try to access this lock after I finalize it. OK, so this is the basic reasoning idea. Now, again, I'm not going to show you the full logic, but let's see at least when I'm going to have a logic or the analysis, I'm going to have some model for these local states of threads and resource invariants, some semantic domain for them. So for example, before these resource invariants and local states describe just sets of heaps of the program. And the heaps are finite partial mappings from memory locations to the values they store. So finite and partial because some memory cells are allocated and some are not. OK, so now let's try to devise something like this, some semantical model like this, for the local states of threads and resource invariants in this case. So in this case, I'm going to have two types of locations, either the ordinary ones that store values or the ones that store locks, right? So I'm going to have disjoint compositions here. Now, what is a lock? Well, a lock is something that tells me whether it's locked or unlocked, right? Then I'll also have to associate a permission with this lock, how much of the lock I own. And I'm going to have to associate an invariant for this lock. OK. And what is an invariant? Well, an invariant is just a power set of heaps. It's a predicate on heaps. And that's basically the definition. So we have heaps defined in terms of locks, locks defined in terms of invariants, and invariants defined in terms of heaps. Well, it happens that there is a problem with this definition in that this circularity is not well formed. We've just hit a set cardinality paradox. That is, there are no sets that would satisfy these equations. And that's because the cardinality of the power set of heaps is strictly bigger than the cardinality of heaps. So the expression on the right-hand side here has a strictly bigger cardinality than the expression on the left-hand side. And this definition is just inconsistent. And the underlying reason for this paradox is that locks here in this picture can refer to other locks via their resource invariant. The lock protecting this resource invariant may know about the existence of this lock, and so that's why you get this circularity. OK, so the first attempt doesn't work. Let's try to repair it. Well, the main idea why the problem here arose is that we just have too many invariants. We said that the invariants are the power set of heaps, and that's too big a set to be consistent. So the way we can repair it is we can say, before doing a proof of a program, I'll fix how many invariants I need. And I'm going to give names to these invariants. I'm going to fix a set of names for invariants. Now, this set, it doesn't have to be finite or countable, but it has to be of a prefix cardinality before I'm going to do a proof. And now, instead of referring to invariants directly in locks here, I'm going to refer to invariants by name. So I'm going to say, OK, now locks are defined in terms of names. And so in this picture, this corresponds to annotating every lock with a name and every partition with a name corresponding to its invariant. And now I don't get any circularity. This domain construction is OK because names we have names and a circular definition. Heaps are defined in terms of locks. Locks are defined in terms of names. And invariants are power set of heaps. So everything is fine. Now, before doing a proof, as a part of it, I'm going to have to associate with every name a corresponding invariant. So every proof will come with a table here that tells me for every name what its invariant is. And the invariant is just a power set of heaps. And so in this way, I'm able to avoid this circularity. Now, the way the logic will work is, for example, the concurrent separation logics rule for the lock command basically told me that I'm conjoining the resource invariants to my local state. Now things will become just a bit more complicated. So before locking a lock at the address E in the memory, I'll have to have some kind of a permission for this lock. That is, so what this says is I have a lock at the address E. I know that this lock exists. It has the name A. And by looking at this name, I can tell the invariant of this lock. And it comes with a permission pi, which is this number. And then after I lock the lock, I get the ownership of its resource invariant, I, associated with the name A. Now, it happens that it's usually useful to parameterize the resource invariants with the address at which the lock is allocated, E, so I get it here. And I also get some fact that tells me that I actually hold the lock that will come useful when I try to release it. So that's the way the logic works. Now, what are the pros and cons of this solution? The good thing is that the analysis for this model is very similar to the one for static locks. You just infer an invariant for every name, so automation is not a problem. The bad thing is that in this way we can't give specifications to code that's generic in the resource invariants, because we always have to refer to a particular resource invariant by name. And this is not a problem usually for verifying closed programs, but it may be a problem for verifying generic libraries. And this particular problem has been fixed recently by Aquinas, Hubor, and others, but unfortunately at the price of drastically complicating the semantics. Okay, so to conclude, what I've presented to you is a thread-modular shape analysis that's automatic, sound, and efficient. It handles dynamic local allocation, and it produces proofs in a program logic. And there are a few things that I haven't covered, but you can talk to me about them offline. So I haven't covered dynamic thread creation, interprocedural analysis, and liveness. And before I finish, let me just say a few words about some future directions. Okay, so this analysis that I've just shown you and the logics work for programs where there is this heap splitting. There is some notion of ownership of parts of the heap by locks and threads. And this is fine for coarse-grained programs, for example, and for some of the fine-grained programs. But this is not fine for non-blocking algorithms or for most of the fine-grained algorithms, programs that use lower-level synchronization techniques. And the underlying reason is that really invariant-based ownership reasoning doesn't work for these programs. You need more expressive mechanisms to express interference specifications in your logic. Typically, you need something like relations. And recently, there's been quite a bit of work on this. So two groups of people independently proposed a combination of lie guarantee reasoning and separation logic that can actually be used to verify complex non-blocking algorithms. But unfortunately, these logics deal with only basically one shared data structure. They have very awkward reasoning in the case when programs are allocating dynamically many data structures, like the programs with storable logs, for example, the dynamically allocated logs. And so really, you want a combination of these two approaches. And this is one direction that is currently being investigated here. Okay. The other thing is, so is the problem of concurrency solved? I've presented you some good methods, so what's the deal? Not quite, and really, I think there are no practical and scalable and sound verification methods for a wide range of concurrent programs. What I mean by that is that for sequential programs, we have tools like static driver verifier that for a particular class of applications just work. Unfortunately, we don't have any comparable tools for concurrency, and that's because there is no critical mass of methods that would allow you to build such a tool. So, for example, I've presented you some methods for handling heap manipulation that are being used as a basis for a practical tool, but we haven't had so much success with arithmetic properties, with properties dependent on arithmetic computations in concurrent setting. And this is needed to build, say, a tool like static driver verifier for concurrency. Now, I've done some work on verifying liveness properties of non-blocking algorithms, which is a restricted class of concurrent programs. But liveness properties of programs with locks, for example, are a big open problem at the moment. Finally, I've talked about log-based synchronization. I guess that what I've told you generalizes to message passing, but it remains to be seen that whether it's of any use for verifying, say, distributed systems. And finally, I've talked about methods that are thread-modular. They consider every thread in isolation. But to be really scalable, I think you need to go intra-thread modular. And what I mean by that is you have to consider parts of a given thread in isolation, say, only a concurrent library in isolation, not the whole thread. And finally, I think that the synergy of program logics and program analyses that I've demonstrated to you can actually be taken further to verify more sophisticated properties. And I'm in particular interested about information flow properties and performance properties. And I think it should also be useful in handling advanced language features. For example, the issues with dynamically allocated logs that I've shown you, these paradoxes that arise in semantical models, are similar to the ones that arise when you try to handle functional features in programming languages, like higher order and storable code. Again, it remains to be seen whether similar methods can be devised for handling functional features in modern programming languages, for example, in F# or in C#. And that's it. Thank you.
I had a question about the dynamic logs, and you said they had a permission associated with it, which said how much part of that log is associated with that thread.
Mm-hmm.
If it's a dynamic log, and how do you figure that out? Is that easy or?
Intuitively, what this encodes is which threads are allowed to acquire this log. So in principle, you might imagine allocating a log, allocating a data structure, instantiating several worker threads, and then giving a permission to access this log, to acquire this log to every one of these threads. So this permission splitting is something that you would have to do during the proof of your program in the logic, and given by this intuition of what who the programmer thinks should access this log. Or you should somehow, in what we do in the analysis is, we would use some, again, application-based heuristics that would say, for example, well, this class of applications typically does use this parent with worker threads, so this is how we're going to split permissions.
So if the permissions are wrong for some reason, will that, so if it's a heuristic, then can we be assured that so for example, if for a static log, I can understand that you could sort of easily find out which threads access which log.
Mm-hmm.
It's a dynamic log. Can we be sure that this is how the permissions are?
No, we can never be sure. I mean, if you get the permissions wrong, you will get a false bug in the analysis. Typically, to be more concrete, for example, when you fork a thread, you will use, again, these reachability heuristics to decide which part of your local state to give to this thread. If this part of the local state happens to contain some permissions for the logs, for example, you've passed this log the address of this log as a parameter to this thread, then you will give some permission to this thread to access this log. Yep.
Could you tell us more about why liveness of log-based programs are high?
Yes, I can. So they're hard because it's unclear what the interference specification should be in that case. So for non-blocking algorithms, the way we resolved the problem is we did rely guarantee proofs where the interference specifications, the rely guarantee conditions, are of a very, very restricted form. They just say certain things don't happen infinitely often. Now, if you want to prove the same thing for log-based programs, then you need more complicated assumptions. For example, response properties. If I acquire this log eventually, I will release it. With some supporting safety properties. So actually, if you just try to do the proof of a producer-consumer, you'll get a modular proof. That's still quite complicated.
But you still have non-interference, right? Once you acquire the log, it's like a sequential program. You own all the memory that you're going to access, and so you can do sequential analysis to prove termination of that.
No, but so that's for the dynamically allocated logs. For non-blocking algorithms, as I said before, the invariant-based approaches don't work. So when I on the slide I said that I applied my methods to verify liveness of non-blocking algorithms, I cheated in that I didn't apply this analysis. I applied its generalization to infer relations, and so there it's much more. Everything is much more complicated.
So you use the concurrent separation logic a variation of that to prove this thread-modular shape analysis, right? Mm-hmm. So let's say if I don't use separation logic and I use some other shape analysis like TVLA or first-order logic-based, what part of the reasoning would become hard? I mean, for example, you had to sort of invent a new logic and do its soundness and so on, right?
No.
So-
Oh, sorry.
Okay. So I was hoping that if you use a first-order classical logic-based approach, where you have like disjointness information, you can express disjointness by some quantifiers or something. What part of the analysis would become sort of more involved?
So when I presented to you the analysis, I said it takes a sequential shape analysis of the parameter satisfying certain conditions. And this is actually indeed so. So if you take a sequential shape analysis, and another example would be, say, an analysis based on shape graphs, not quite TVLA, but shape graph-based analysis, then you can fit it into this framework. So all these results are generic in that they say, well, you have some abstract domain satisfying these conditions. If you satisfy them, it's fine. The logic is sound and the analysis is sound. So again, the logic is also proved with respect to a generic abstract model, typically. Now, as for how practical this is, so TVLA is definitely not in, but shape graph analyses are in if you hack them a bit. What you really need from your analysis is the ability to handle dangling pointers. Because when you split the heap, you usually, even if your program doesn't have the disposal operation, when you split the heap, you do introduce dangling pointers. And it happens that not so many analyses satisfy these conditions, but you can usually, not TVLA, but like shape graphs, you can usually hack them to add this treatment. So that's okay.
About what about the interest thread verification that you said? Why don't you have that already? I mean, you would verify one method and you would follow or even each statement, right?
Well, I should be more precise about what I mean by that. What I mean by that is, for example, I have a very highly concurrent concurrency library with some fine-grained synchronization, and I have no idea what's going on, and I verified it using some very complicated methods. And then I have a coarse-grained client that's really simple. Now, when I reason about this client, suppose I'm doing rely guarantee, and I'll have to have some specification of the interference. I don't want to reason about what interference is being caused by this library, because I've already verified it. That's okay. But it happens that devising proof rules for of this kind may be quite challenging. For example, to assume. So what I want to do, for example, is I want to assume that a call to this library is an atomic operation in my reasoning. There is no interleaving going on there, even though I know it's not true. And this will only be the case if this library is linearizable or sequentially sequentially consistent, but then I have to put some conditions on the client. So there is a recent paper by Honsok Yang and Noam Renetsky from Peter Hearn's group who proved mathematical results could eventually lead to such a proof system. So really you have to devise atomicity refinement proof rules, and this may be quite difficult.
Okay. So Alexei is going to be here today and tomorrow, and we have a schedule set up to speak with many of you. He's also going to be here Thursday and most of Friday, so if you're not in the schedule for the next 2 days, I'm going to call